Okay, so moving on to this. This is just a very short introductory set of notes trying to describe basically, what are we talking about when we say machine learning? Okay, so let's first talk about tasks that we might want to perform. And I'm going to focus on these three because these are tasks that we will spend considerable time on in the term. There are many other tasks for machine learning that are out there, and unfortunately, in just a one semester course, we cannot cover them all. So there's definitely other ones, but let's focus on these three for now. And these are tasks that are very, very broad and generic. They show up in engineering, science, medicine, business, all sorts of different fields. Okay, so we're going to focus on prediction. You can kind of guess what that means from the name, right? But another name that means the same thing, which you may not know, is regression. So when we talk about regression, that's basically just prediction. That's the statistician's name for prediction. Then we have classification, which I'll get into, and then categorization, but categorization is mainly known as clustering. But you might not know what clustering means, but if you say, I want to categorize these things, that's essentially what you're doing. Okay, so let's talk about these just from a few examples. So one type of prediction task would be predicting a stock price in the future. So, in that case, there's one stock you're looking at. You're looking at some time in the future, and you want to know, maybe it's tomorrow, you want to know what is the price going to be tomorrow because, hey, you want to invest money in it or sell or whatever. And so to predict that, you're going to have to use some existing data that you have today. So that could be many things, right? So what are some examples of data that we could use to predict a stock price tomorrow or in a week? Yeah.
Just the prices from the past month.
Yeah, the prices from today and previous. What else? Is that all? Volume? Sure. Volume. What else? News, exactly. It doesn't have to be numerical. It could be articles, right? If you have a smart enough system that can read news articles and get relevant information from them, that's also valid too. Any other ideas?
The prices of stocks and related.
Yeah, exactly. Related stocks, all that stuff. So it's pretty generic. That's the point. Is like the kind of data set that you can use to predict is quite generic. So now the question is, okay, well, how are we going to do that? How are we going to do the prediction? Once we have this data, we know what our task is, our goal is. So you could say that there's kind of a classical approach, which maybe people would have used, 50 years ago, which is that you have some expert that says that they understand stocks, the economy. They have this kind of special knowledge. They have mathematical models, and you would then apply their models to this problem, right? So it's based on kind of knowledge. It's not based on learning. It's based on, you assume that they've figured it out, and then you use that. But that doesn't actually work that well, using some sort of economic theory to invest in the stock market. So another way to do this is like we said, take the data. You have all this data, and you can run this experiment many times. You can look at using yesterday's data for today. You can look at today's data for tomorrow, tomorrow's data for the next day, and so on. And if you do this many, many, many times, you can eventually see patterns. And if you can learn those patterns and learn it automatically, you can build a model that has learned. It wasn't told this is the way the stock market works. It learns how the stock market works. And it's applying that knowledge for prediction. Okay, so do you see the distinction between kind of that classical approach where you rely on an expert and this learned approach where there is no expert, all you have is the data? That's kind of the gist of machine learning. Any questions on this? Okay. Let's talk about classification, another example. So the difference between classification and regression is similar, except that in regression or prediction, the value that you are trying to predict is a number from a continuum, like a real number, complex number, or maybe a set of them. Whereas for classification, it comes from a discrete set. So basically, maybe we have handwritten digits 0 through 9. So there's 10 of them total. And here are examples. These are like some examples of zeros, some examples of ones, some examples of twos, and so on. And you can see there's a lot of variety in there. But your goal is that you're given one of these, and you're asked to tell what digit that is. So that's the problem. So you're predicting something, but in a discrete set, 0 through 9. And again, now the data set you're given, the data for prediction is just going to be this little small image. And that image, as we'll talk about later, you can think of as a matrix of brightnesses, or you could vectorize it if you want, but that's what you're working with. So here again, you could imagine trying to do a classical approach to this, where you say, okay, well, I know a 0 is like a circle and a 1 is like a line, and so you could try to make up some sort of mathematical model for what these things are. But then, as you can see, it's a little bit challenging in applying that model to that little image you get, right? Because some of these examples are actually pretty tough. Like, I don't know, like this one, is this a 1 or a 9 or a 7? It could be any of them, right? So essentially, here again, rather than coming up with some model of what a 1 is or 0 is and then trying to apply that, you could do it in a way that essentially we as humans do it. You know, we, from a young age, have been seeing examples of these things, and we have kind of learned in our brains to figure out, you know, when I see this, what does it mean? And we've just done that from seeing examples. So we could do the same thing with a computer. We feed the computer enough examples of this paired with the true ground truth that this was a 6, and eventually it learns its own way of figuring out how to map that little image to a number between 0 and 9. So that's that learning from data. Okay, any questions? All right, so this is actually a very, very popular toy data set, MNIST, that we'll see and we'll use later in the course several times. Okay. All right, so this third task is clustering, or you can think of it as categorization. It has kind of a different flavor. The problem is like this, and this is just one example. Imagine that someone gave you a collection of text documents, just this random collection, and they want you to categorize them. Like, okay, these are maybe about sports, these are about news, these are about mathematics, or whatever. But you don't know what the category should be in advance. All you know is that you're looking to group examples of your data into little sets that are similar within the set and different across the sets. So that's really what you're doing at the end. And you hope that by doing that, you get categories that have a meaningful order to them. So that's a text example. Maybe a simpler example is if you just have pairs of numbers like x, y. So this is like x, this is like y. So each one of these dots is just one example of an xy pair. You're given, let's say, 100 examples of xy pairs, and you're asked to group them to cluster them. So what you could do is you can plot them on a 2D plane like this, and now, as a human, you look at this, and some clusters pop out, right? These all seem to be related, these seem to be related, and so on. So we're looking to do that, but automatically. In order to do that, we need to have a clear definition of the criteria we use for clustering, and there's no perfect definition of that. There's many different forms of it that people have used, people find work well. And so we're going to investigate a number of very different ones later in the course. Okay, so these are just all examples of what kind of tasks we might want to perform and the difference between machine learning and traditional approaches. Yes?
How would you differentiate classification and clustering?
So in classification, you have a pair of like data and target. So you're training, when you see these examples, You have like, this is the data and this is what I'm trying to predict. In clustering, you have no target. You just have examples of this data. So, so for example, just coming back to the text example, you could make a classification version of this where someone gives you like a bunch of documents, but they also tell you, oh, this is a news document, this is a math document, this is a religious document, and then you could train a system that takes in a document and predicts what the label is. It predicts this is the type. But clustering is very different. You're never told what the ground truth is. You're just given a bunch of documents and you're told, arrange them in a way that these ones are similar to each other, these other ones are similar to each other but different than the first, and so on.
So isn't the classification which is classifying these clusters in?
No, because in classification, you're given two things for training. You're given the data and you're given the target. In clustering, there's no target. Yeah. So, I mean, another way to say it is like in this picture. Let me use different colors here for the different clusters. Okay, if I had one more color, I could do the last one. But so here, as a result of the clustering, we're able to color these. We're able to say that these are all red, these are all blue, these are all green. As a result of the clustering, no one told us in advance any labels, right? If this was a classification problem, during training, each of these would be colored red, each of these would be colored blue, each of these would be colored green, and then during what we call inference, or when you apply it, you'd get a new point without a color, and now you're asked, what color is it? So that's the difference.
So for clustering, could different models cluster in different groups?
Yes, different models, different definitions of, because the clustering is kind of, you rely on some definition of some mathematical problem you're trying to solve. There's different definitions that will lead to different results, different performances, different metrics. Yeah. Was there another question? Yeah.
Yeah, you reminds me of supervised learning and unsupervised learning.
Exactly. Clustering is an example of unsupervised learning, whereas classification and regression are examples of supervised learning. There's other examples of unsupervised learning that we'll talk about in addition. But in terms of supervised learning, yeah, we're going to focus on these two. Okay, great questions. Any other questions? Okay. All right, so, so I talked about this a little bit already. The traditional approach, classical approach, is you obtain some sort of model from a scientific expert or business expert or whatever, and then you apply that model to your task. And there are times when this is exactly what you want to do. Like if you want to design a circuit, you want to use Ohm's law, right? You want to use that basic knowledge. You don't have to reinvent the wheel, so to speak, to design a circuit. On the other hand, there's other cases where there's problems with applying models. So first of all, maybe there is no good model, like the stock market. There's a lot of theories, but none of them really work that well. Because if there was one that always worked well, then everyone would use it, and then the market would change so that wouldn't work anymore. Okay? But there's other cases, like a good scientific model may exist, but it might depend on so many parameters that it doesn't really work out. So let me give you an example of that. So in this room, my voice is bouncing on the walls, the ceiling, bouncing on all of you sitting in your seats, and eventually landing in each of your ears. So there's all these echoes and so on. You might say, okay, I wish I could remove those echoes so you could hear me better. But how do you do that? So the physics behind all of this stuff is pretty well known. It's relatively simple. But the problem is that if you really want to apply that physics directly and say, well, I want to cancel this path and that path, you have to know exactly where all the walls are where I am, where you are, where all the other people are, all the reflecting surfaces. You have to know all that information to directly apply the acoustical models. Okay, so the model is there, it's just not convenient to use. So when you put on like noise canceling headphones, it's not using any of that. It's actually learning a model on the fly. It does it by coming up with one particular reference signal. It's basically like a regression problem. It comes up with one reference signal in a place that it thinks is probably not corrupted by noise, and then it tries to, or sometimes it's purely corrupted by noise, and then it uses that reference as well as what's impinging on your ear to try to cancel the interference. So noise canceling is definitely an example of learning. It's something it's actually one of the very first examples. In the 50s already they were doing it, and they were doing it with tubes and actually mechanical circuits, and it was crazy what they had to do, but it was like the very beginning of learning. So there's various reasons why sometimes we would like to use learning instead of some expert-driven models. Okay. And finally, now we'll get into a little bit of math, and it's okay if you don't understand all this. I'm just giving you a little bit of flavor of stuff that at the end of the term, hopefully you would see this stuff and you understand everything. But let's try to formalize what I just described using some mathematical notation and concepts. So essentially, these are the key ingredients of machine learning then in the mathematical sense. We're going to have a modeling function. This is going to be the thing that's doing our prediction, our classification, and so on. So this is going to take in our data and output, what we want. It's going to do our prediction. But that modeling function is going to depend on many, many adjustable parameters, and these are the things we need to learn. You could kind of say like your brain is a modeling function. It has all these neurons which are connected together, and those are all the things you have to connect in the right way for your brain to do something useful. So there might be millions of parameters to adjust. Okay, now a loss function is used to know how well a given set of parameters is doing. So it measures goodness. So like when you have an untrained system, it's probably not going to work well at all. It would have a very high loss. You eventually want to drive that loss small, and so you have to define a way to measure how good things are working. So like with the stock market, you could say, well, this is the actual value, this is what I'm predicting. You want to minimize the difference. You could minimize the squared difference, you could minimize the absolute value of the difference. There's different choices in that loss. But it's some way to concretely say, how good your model is performing. Okay, now you need a training data set. You need to see many, many examples in order to train your model. And then finally, you need an optimization algorithm, which is going to figure out how to adjust those parameters theta to minimize the loss on average over your training data set. That's how it all comes together. So here's again stock and market prediction. Let's say we take our currently available data, and we're just going to assume it's a bunch of scalars. Maybe these are the previous values of that stock, like today and yesterday and the day before and so on. We'll collect D of them together. We'll stack those scalar numbers into a vector. So in all my notes, I use boldface for vectors, lowercase boldface, whereas I use non-boldface for scalars here. And all my vectors will always be column vectors, unless you put so you always know that X is a column. If you want to make it a row, you put a transpose on it. Okay, just to keep it straight, so you don't have to guess, is this a row or a column? You know what it is. Okay, the modeling function, again, takes in this X as input, takes in your data as input, and outputs an estimate of Y. Y is the future stock price. It's the thing we're trying to predict. Okay, so how do you build this modeling function? That's one of the main questions of the course. As we go through the course, we will see many, many different ways to build it, starting with simple, getting more and more complex. So at the end, we'll be talking about deep neural networks, which are complex. They could involve millions of parameters, but there's sort of a recipe to building them. The loss function, again, quantifies the accuracy of our model, how well it's performing. Again, for stock price prediction, we can say that Y is the true stock price, Y hat is our estimate. Our loss then compares these two things. Typical comparisons are you take the difference and square it, or you take the difference and look at its absolute value. The data set, in this case being a supervised machine learning problem, has pairs of input, output. And here it has n different pairs. Each pair is indexed by the integer I. Okay, so n generally, you want this as large as possible. So this is many past examples of how these inputs relate to the outputs. And hopefully, if you see enough of these examples, you can figure out how to adjust the thetas so that F mimics those examples. And finally, the optimization algorithm is the thing that finds that. So here's where we put everything together. So again, F is our predictor. We put in the ith training example. Out comes an estimate of the ith training target. We then look at the difference between yi hat and yi. We might square it. And that's what we have for the ith example, but then we want to average this over all of our examples. This gives us what we call a cost function and something that we want to make small. So we're going to formulate an optimization problem. So this means, minimum. The arg means that you're looking for the minimizer. You're looking for the value of theta that minimizes this. If you didn't have the arg there, this would refer to the smallest value that your loss takes. So the arg is not saying the minimum, it's saying the minimizer. You're looking for the theta that achieves the minimum. And we can call that theta hat. Once we have learned a good theta hat, we just plug that one into our model, and now we can just apply this model. Tomorrow we'll get a bunch of data, we'll stick it in that model, and we'll get an estimate of the next day's stocks. So this is kind of in a nutshell what we're doing as we go through the course. We're going to learn all kinds of ways of designing this modeling function, the loss function, algorithms to optimize. And again, there'll be different tasks. Maybe we're doing prediction, regression, classification, categorization, clustering. And that's not all. We'll be learning about other really important concepts, things like generalization, regularization, ensembling, PCA, non-negative matrix factorization, Gaussian mixture models, expectation maximization, and so on. So lots of really important little concepts that are kind of related to this, woven through it, but also kind of different. So again, the main things are concepts in mathematics are super important. At the same time, knowing how to implement them in software is super important. You really need both of them to do machine learning well. We talked about these prerequisites. We talked about homework 0 as giving you linear algebra review. And there's going to be a short Carmen quiz for linear algebra to just sort of test your knowledge. So I guess one other thing I'll add here. This is not an easy course. There's a lot of work in this course. So I want you guys to know that now. If you're just looking for like a casual course just to get a few more hours, this is probably not the course. So I already told you, right? Every week, homework, lab, quiz, all throughout the term, unless it's an exam week. So basically, students tell me, the students who really want to learn machine learning, they tell me they love this course. It was awesome. But there's students that maybe just wanted a few more hours, and then a few weeks in, they're like, I don't know if I should have taken this course. It's a lot. So, you guys can make an informed choice right now. If you're excited about machine learning, you want to learn about it, you want to put in the effort, it's a great course. But if this is just your last semester and you just need a few more hours, may not be the best course. So, all right. Any other questions on anything? Yes?
Yeah, could you go back to page 11?
Page 11, sure.
And then you talk about loss function.
Yes.
And I noticed you have two different choices, minimizing L2 node and L1 node, and it's out to the user. And then my question is that in our course, the convention estimate value minus the nominal value or the other way around? y hat minus y, because the result is gonna be the same.
Yeah, if you swap them, nothing changes because the absolute value will cancel the negative, and so will the square.
Yeah, because even given course, I mean, after the given course, the value, I mean, the convention is a bit different.
Okay, yeah, so here, for this, I think it's pretty clear. It doesn't matter what the ordering is. You can swap them and you get the same value. Is there another question? Yes.
Yeah, I know you talked about deep learning and classification. Do you cover convolutional neural networks?
Yes, we'll be doing a lot with convolutional neural networks, Unit 9. Yeah, kind of the course in some sense builds all the way up from units 0 all the way through 9. We just keep building on prior stuff. We eventually kind of get to that. And then after that, we're going to look at that's all kind of supervised learning. And then we're going to look into some other like clustering and other topics after that. That's probably, I don't know, I would say maybe 60% in, 70% into the course. That's where you'll see all that. PyTorch, deep networks, convolutional networks, all that stuff. Is there another question? Yeah.
That quiz over the linear algebra stuff, is that going to be next Fridays?
Let's see. Does anybody remember when the quiz deadline is? I think I maybe I didn't post. No, I didn't post it yet. Yeah. Yeah, I think I'll have that due probably on Friday in a week. Give you a little bit of time. Yeah. So I really do recommend taking that seriously. Looking through this review, if the material seems really uncomfortable to you, you basically have two options. You can try to speed learn it now, or another option, this course is taught every term. If you feel like you want to take a linear algebra course first and come back to this course next term, that's what a lot of students do in the end. But it is really important stuff. Other questions? Yes?
So the lab, are we ready to do we have funding something at the end of the lab session? Or?
So the lab is not something that meets in a room or anything. It's something you do on your own free time. So you can do it with colleagues, or you can do it on your own. You can do it on any computer you want. You just submit it by midnight on Friday. That's it. Okay. Thanks, guys. Look forward to seeing you on Friday.